So welcome back, everybody. Welcome to the Flavor and Precision Session 1. As you can see, we have 3 talks. Talks are 30 minutes plus 5 minutes of question. Just as a reminder, if you have questions, please type them into the Q&A window, and I will read them from there. And you can also ask questions on the Slack channel. So let's start with our first speaker, Yuval Grossman, and he will tell us about flavor and precision physics, a theory overview. So Yuval, please go ahead and share your screen.
Okay, thanks. Share. And okay, hope everybody can see it.
That looks good.
Looks good. Okay, good. Okay, thanks everybody. And I plan to give some review of flavor physics and where we are on that. So let me jump directly into the talk. And I start with this picture. And I know at this webinar, I don't even see, faces of anybody. However, let me make the assumption that all of you seen some kind of this version of this picture before. And most of the time, since you've seen this picture so many times, it's just, like, okay, I've seen it. Like, why you even show this picture? We all seen it. What's the big deal? And what I like to make is the following point, is that actually this picture is amazing and it summarizes everything. And we all know it. I mean, it's not like something that nobody told us before. Wow, this picture is amazing. But sometimes I feel that we a little bit forgetting about how amazing this picture is. Okay? So, I say, let's take 1 minute just to stare at this picture, enjoy the beauty of all what we see here. And I be quiet, but I cannot be quiet, so I will not do it. But what we are seeing here is, I would say that's the status of flavor physics. Flavor physics is basically doing amazing. I mean, you just make so many measurements and basically they all agree. And we get this tiny, tiny overlap window of so many different measurements. That's where flavor physics is. Okay, so while we're going to talk about all the issues with flavor physics soon and later, there's still, the big picture is this, and that's why it's such a big picture. Flavor physics is doing great. So what are the goals of flavor physics? And I will talk about what I see as 2 major goals of flavor physics. And the first goal is the one that we kind of all know, and again, I'm sure everybody of you heard this already so many times, is to find hints for physics beyond the standard model. And this is kind of a zoom in into this area, and this kind of purple region is something that I add on. And maybe in 10 years, that's where we're going to be. We're going to actually look for this kind of picture and we find that there's some disagreement. Okay, so that's goal number 1 of flavor physics. Goal number 1 of flavor physics is to get us more and more precise, both experimentally and theoretically, in order to actually see some deviation between those two pictures. And one question we like to ask about it is, are we seeing the tails? And when I say, what do I mean by seeing the tail? Are we already seeing the tail of the BSM? Are we already start seeing the deviation from the standard model? And of course, there's a lot of what we call B-flavor anomalies. And I will not touch on them because we have Gudrun going to spend a whole talk only about the anomalies. So I will not talk about them. But the big picture question is, are any of those anomalies, or some of those anomalies actually, maybe they are the tail of the BSM physics? Do we see kind of the beginning of the big whale and we see only the signals? My personal point of view is that none of them are convincing enough for me at this point, but of course it's very exciting and we're going to have a whole talk about it, and I will not touch on it. And now let me move in what I call the second goal of flavor physics, and that's what I call the weak-strong interplay. And traditionally, the story of QCD was that we have to kind of overcome QCD, right? I remember giving these talks that I say, QCD is this strong, bad bully who made all the problems for us. because they totally mask our ability to get into the weak physics that we really care. This nice, interesting, perturbatively weak physics that is all masked by this crazy QCD stuff that we are seeing. Okay, and then that's how we did flavor physics, and that we are keep doing it, is to find ways to kind of get around QCD, right? We use some approximate symmetries of QCD like isospin and SU3 to get around it. We find some cool, neat ideas to actually measure some of the QCD parameters. We use the lattice, we use some other models or techniques that we have, OPE, whatever we can. Everything we do in flavor physics, basically everything we do in flavor physics is this big, quick picture. How we eliminate QCD, how we can really get into the weak interaction and overcome QCD. And I would say that, so that was in the past, and we still have it. It's not that it's going to be something else, but I think that there's actually something new in flavor physics, something that is emerging in the last few years. Is actually we use the weak interaction to probe QCD. That is, we know the weak interaction. We basically measure the parameters of the weak interaction very, very well. And we use this as an input to something. And as a result, we actually measure some QCD amplitudes. And by measuring those QCD amplitudes, by measuring QCD parameters, we actually learn about QCD. We say, you know what? We are not going to try to calculate you, Mr. QCD. All we're going to do is just to measure you. And once we measure, we really understand what's going on. Okay, and I think that's a little different angle of what we are doing in flavor physics that I start to understand in the last few years. Flavor physics is not only to get understanding of the weak interaction and beyond the weak interaction, it's only actually using the weak interaction to learn something interesting about QCD. So that was like my idea of where we are on this, is to see those two aspects of the future of flavor physics. So what I'm going to do in these talks, I'm going to give, I would say, a biased sample of ideas on both directions. And it is biased because I will talk about my own work. I guess it's biased because I just know it the best, and I'm probably more excited. That's how it is. We're more excited about our own work, but it's just example that I really feel good about that I can explain. And I'm going to give 3 examples, one in beef physics, one in charm physics, and one in kaon physics. And where we actually, and in each example, we're going to see either how we're going to learn how we actually probe BSM physics and or actually get some understanding of QCD. So let's start. And our first example is going to be B physics. And B physics, I will describe it, I will say it's not a teenager anymore, okay? It's been around for a while, and it's already, understand, we learn quite a lot from B physics. However, there's still quite a lot of going on. It's still just somewhere between getting into real maturity. So what next for B physics? So the first thing is, of course, the anomalies. And as I said, we're going to have Gudrun going to talk about it in her talk. We're going to have much more data with clean. There's a lot of clean things that we can actually do on flavor physics. And we both have LHCb and BEL2 who are running, and they are both running quite well. As far as I know, they are doing actually very well. So on one hand, we are going to expect much more data, both hadronic from hadronic machine and from E+ E- machine. And there's also a lot of theory development that are keep coming. There are always some new developments. So hopefully the future is quite bright. And in 10 years, we're actually going to get much better understanding of what's going on. So what I'm going to do as an example of understanding better both QCD aspect of using flavor physics and understanding better the weak interaction, I'm going to talk about the status of SU3 subrules. So what is the basic idea beyond SU3 subrules? The basic idea is that we use the approximate symmetries of QCD, like isospin or SU3. In particular, I want to talk about U-spin. And we use isospin in many places because it's a very good symmetry. The breaking is of order 1%. So when we have precision measurement of order 2 or 3%, experimentally, then we can use isospin and we are all fine. Okay. SU3, on the other hand, or just U-spin, is useful, but it comes with loud breaking of order 20%, or maybe 30%. And in those days, if someone comes and says, look, I have this measurement with a 30% error, in the regime of B physics, that's usually not good enough. in B physics, we are down to a few percent level experimental precision. So if our theory can only do 20 or 30%, it's not very useful. So the question is, what can we use SU3 for? And that's what I'm going to talk about. So one thing that we can use it is to estimate isospin breaking effect, and people were doing it. Or sometimes you say, you know what, it's okay with rough prediction. That's actually, we can see some pattern with rough prediction. And I'm going to talk about some of it when I talk about charm physics. The cool stuff is maybe we can actually get precise physics with SU3. And how do you get precise physics with SU3? We use the amazing fact that when you take a small number and take it to a high power, it's become tiny. So if you take 20% and take it to the 5th power, you get a tiny number. So the question is, can we actually use SU3 not a leading order, but actually use SU3 to higher order and make some prediction, some actually measurement where we have something that is valid to 2nd order or maybe 3rd order or 4th order in SU3, and then you get precision measurement. Okay, so that's the basic idea. So we actually have a paper that I'm kind of excited about that is in the making, and I'm going to just tell you the result, and without getting into the detail that will take a little too long, but we kind of understand what's going on, okay? So the idea is that we can actually get those U-spin sum rules that are valid not to leading order, you can actually calculate to any order that the system allow it, okay? And what we find that in any system that we have, we can actually know up to what order we can get it. So in some simple system, you can only work to 1st order. There's no sum rules that you can do to 2nd order. However, there's some cases that you can go to 2nd order and you can go to 3rd order, okay? And what we found a really cool way to actually take the system and map it into some multidimensional lattice, and you don't have to do any calculation like we used to do in the past, and we can actually get all those sum rules, okay? And with those sum rules, eventually, hopefully, we can actually make precision measurement using SU3. So I don't know how practical it will be. As of now, it doesn't look to me very practical, but I'm not losing hope. But this is just an example of what we are talking about. What we are talking about, once we actually get those U-spin sum rules, we can actually get some more precise determination of weak parameters, and we're going to understand something about QCD, for example, about U-spin breaking, and about values of some hadronic matrix element. So that was one example. That was the example from B physics. Now I would like to move on and discuss charm physics. And charm physics, in particular CP violation in charm physics, which I want to describe, it's a baby, okay? It was born in 2019 when LHCb, for the first time, got the 5 sigma determination of CP violation, and what they measure is the by now famous delta ECP, which is the difference in the CP violation in the K plus K minus versus the pi plus pi minus decay of the D0, and the number that they got is something of order 10 to the minus 3. So I don't care too much about precision, just the rough number is 10 to the minus 3. So what is next for charm CP violation, okay? And again, just the 2 points that I was making before, we can actually use both of them using charm. We can learn something about QCD from charm physics, and I'm going to explain it. And we can also actually use some SU3 prediction to test the standard model for future determination of charm physics. So let me start with the first point, and that's how we can learn from QCD from charm. So for that, let me actually say that when we do charm, we cannot do precision measurement. The problem is that a charm is stuck somewhere in the middle between light and heavy. Long distance physics are totally dominant so many things, like DD bar mixing is totally dominant by QCD, by long distance physics that we cannot calculate. And a lot of the things that we do in also in decays, we just cannot calculate. So what we can do, we can get some rough prediction, which are still useful to learn something about physics. So what we do, we map all the parameters of charm into some map in terms of some small numbers. And here are the small numbers that are relevant when we do charm physics. The first one is basically the non-unitarity of the 2 by 2 CKM. So the 2 by 2 CKM is just the 2 by 2 subblock of the CKM. And to a very good approximation is just the Cabibbo angle, sinus cosine of the Cabibbo angle. But there's a small deviation. And this small deviation is what brings CP violation into the system of charm, which is basically a system of the first two generations. And this non-unitarity of the 2 by 2 CKM is of order 10 to the minus 3. And that's where all CP violations are proportional to this parameter. Another small parameter in charm is SU3 breaking, which is roughly of order 20%. And another one is the Wolfenstein parameterization, which is the famous lambda sinus theta Cabibbo of order 2%, of order 0.2. So for example, if I talk about X, which is delta M over gamma, or Y, which is delta gamma over gamma, and I ask what is the theory. So the theory prediction is that both of them are of order lambda squared epsilon squared, which is of order 0.2%. And experimentally, we measure them. I take credit of what other people do. The community, we have measurements of those. In particular, delta M of the charm system was measured just last week, which was announced by LHCb, the first time that they measure it. And both the delta M and delta gamma, X and Y, of order 0.5%, okay? And when we do charm physics, that's a great thing, okay? 0.2, the prediction, 0.5, the measurement, that's considered head-on. You know, we just got it. Okay, so that's what we talk about understanding QCD and understanding weak interaction. That's the level that we can do things in charm. And when we talk about, for example, delta M and delta gamma in the DD bar system, that's what we are talking about. So now let's move on and discuss CP violation. So what LHCb did when they measure CP violation, they actually look for direct CP violation, and that's interference between D go to K plus K minus and interference between two amplitudes. What are the two amplitudes that we need in order to interfere? The two amplitudes that we need, we can think about them just as tree-level amplitude with rescattering. So we have direct decay of D going to K plus K minus versus decay of D going to pi plus pi minus, where through QCD rescattering, it's become K plus K minus. Everything is tree-level. There's no penguin in what's going on. And the interference is between two parameters that I call lambda S and lambda D, which are actually different in each other by this parameter epsilon non-unitarity that I was just telling you about before. And this is a picture I really like. Many of you probably saw it because I post it in so many of my talks. This is actually a tree that from nature. Actually, I took this picture when we were in Charm 2013 in Hawaii. And what you see here is actually a tree, a biological tree with loops in it. And that's really the way I like to think about charm physics. In charm physics, tree level, it's not tree level in the way that we think about it in graph theory. Tree level is actually, you can produce a pi plus pi minus, and this pi plus pi minus actually rescatter into a K plus K minus, okay? And it's not a loop that you can actually calculate perturbatively, is that what it is? It's a tree level that rescatter into something else, and that's kind of the best picture that I have about this system. So let's kind of look into the system in a little more details. And what we have is as following. We have these two amplitude, the D going to pi pi going to KK versus the direct one. And always we can write this ratio of amplitude as two factors. One is a QCD factor, the magnitude of the ratio and the weak and the phase, and the CKM ratio of CKM parameters and the phase. And the CP violation that LHCb measured is basically this factor. It's the magnitude of the ratio times the sinus of the phase, both for the QCD part and the weak part. So let's look about these four different factors. The first one is the ratio of the QCD factor. It's some QCD stuff that we cannot really calculate from first principle. And then we have the strong phase. The strong phase, since it's some rescattering, it should be order 1. And I think everybody agreed that it should be order 1. Then we look at the other one, the CKM factors. And the CKM factor is, we know it's basically 1 to a very good accuracy. And the weak phase is this epsilon non-unitarity that I told you is the non-unitarity of the 2 by 2 matrix. It's of order 10 to the minus 3. So at the end of the day, what we measure, what LHCb measure is some epsilon non-unitarity, some order 1 factor. So at the end of the day, we know that the CP violation in LHCb should be of order 10 to the minus 3 times some factor that has to do with the ratio of scattering amplitude that we don't know what it is. So what the data imply. Within the standard model, assuming the standard model, the data imply that this ratio is of order 1, because the theory tells us that the CP violation is 10 to the minus 3 times this ratio, and the data tell us it's roughly 10 to the minus 3. So we learned that this ratio is of order 1. Should we be surprised about this? Well, it's rescattering. Rescattering in the GIF system may not be large, but may not be small. And if you look at Kern physics, in Kern physics, rescattering is very large. When you look at B physics, you find that in B physics, rescattering is small. It's of order 10%. What do we expect for charm? It's somewhere between large and 10%. You know, maybe it's 1%. So the way I like to take out of it is that actually we assume large rescattering as which agrees with the data. Okay? We learn something about QCD. So if we take the weak interaction as given, and we take the standard model as given, and we take the strong interaction as the unknown on this story, we find that actually rescattering is large. It's large, it's order 1, and actually it looks quite reasonable to me because it's somewhere between B and K physics, and that's what I would expect naively. So that's the way I like to think about charm CP violation at this point. From large charm CP violation, we learn that it can be done within the standard model, and we learn something about QCD. There's actually some future ideas that we can actually use to look for other decays that we can actually look for it. So now let me talk about the future of charm physics. And the future of charm physics, we can actually look for CP violation in mixing that involves time dependent. And I'm not going to go into the details. What I'm just going to tell you is there's actually a pattern. And this pattern is a rough pattern. It's based only on SU3, but it's actually a very predictive pattern. When we look at CP violation, there's actually 3 terms when we do it, and they have different time dependence. So in principle, we can separate them. This is the direct CP violation, the CP violation in decay I already talked about. That's CP violation in mixing, and that's CP violation in the interference between mixing and decay. And the pattern is as following. The CP violation in the decay is of order 10 to the minus 3, which is, and it's depend on the final state. CP violation in the mixing is universal. It doesn't care about the final state. And the point is that it's actually of order 10 to the minus 4, but it's universal. And then, that's really the cool part. We have the CP violation in the interference between mixing and decay, which is non-universal. However, and that's the standard model prediction, despite the fact that it's non-universal, in the standard model it's approximately universal. It's universal up to order 20%, okay? So we have something to do. We can, hopefully, we can measure several of those decays with the time dependent, and we can check that all of those time dependent asymmetries are universal within 20%. If we find large deviation from universality, that will be a clean test of the standard model. So that's all I wanted to say about charm physics, and let me move on and discuss Kern physics. So Kern physics, in particular Kern CP violation, is mature. It was born in 1964, just a little bit before I was born. I was also born in the end of 1964. So it's mature, but clearly not retirement yet. That's the way I like to think about myself. And there's actually quite a really exciting program going on in Kern physics. And this exciting program is done mainly by NA62 and Koto. And they look for K2 pi Nini bar. And many of you heard about it just because the Koto anomaly came out about 2 years ago. I think it was almost 2 years ago. By now, they found that they underestimate the background. It's still an anomaly, but it's less severe than it was when they first announced it. Okay, so there's actually really interesting Kern physics program that is aimed at getting very clean information. So the big deal about K2 pi Nini bar is that it's extremely clean. You can actually have a very clean theoretical prediction. So what I'd like to talk to you about today is about K2 mu mu. And what about K2 mu mu? It's a rare flavor change in neutral current decay, and it's actually very important in the history of particle physics. The whole idea of the G mechanism came in order to try to understand why we don't have K2 mu mu. And by now, we actually measure K long. The K long was measured, and the branching ratio of K long is of order 10 to the minus 8. And LHCb is now looking to find the K short rate, which the standard prediction is of order 10 to the minus 11. So we are not yet there, but hopefully LHCb can do some Kern physics, kind of a cool result. that I didn't know that LHCb can even do kernel physics. It's really cool. The problem with this is always the same problem is QCD. There's some long distance physics. And because of this long distance physics, we cannot really measure anything nice. So let me say the very basic of K2 mu mu is that we have two angular final state. So the muon is a fermion. So the two muon can be in an S equals 0 or S equals 1. And therefore, the angular momentum between the two muons can be either in L equals 0 or L equals 1 because the kaon is a pseudoscalar. Okay? Now, we can actually do precise calculation in K2 mu mu. And the only precise calculation is on K short into 2 muon in the L equals 0. Everything else that we can calculate is either 0 or we cannot really calculate it precisely. So we have actually one parameter that we can calculate. The question is, what can we do with it? So what is the prediction? So we can actually calculate this L equals 0 final state, and we have a prediction. And we have some numerical value that we know from short distance calculation with hadronic uncertainty that are less than 1%. And then we have here the CKM factors. And that's something we really like. We like to have something that we can measure on the left-hand side that is proportional to something that we know how to calculate time the CKM factors that we are after. In particular, it's proportional to eta, which is the CP violation Wolfenstein parameter. Okay? So we have a theoretically clean determination of eta. The question is, can we measure it? Can we really separate the L equals 0 from the L equals 1? And naively, the answer is no. Why? Because all you have is a muon back-to-back muon, and there's no way you can actually measure the relative angular momentum between them. And therefore, for many, many years, there was not too much attention paid for this decay, the K2 mu mu. However, and that's the big result I'm going to tell you when I talk about new theoretical development, is that we can actually really measure it without the need to separate the L equals 0 from the L equals 1. So how do we do it? We have to look for the time dependent. And I wrote here the time dependent of the decay. And what you see here is the following. You have the CL, which is the K long part. We have the CS, which is the K short part. And then you have interference. This interference must come from CP violation. Okay? And it's come with the sine and the cosine term. And you can actually know how these coefficients are related to the amplitude we are after. So for example, the CL is related to the K long decay amplitude in the L equals 0. The CS part is the K short part, the clean one that we are after, plus some L equal 1 K short decay that we don't know how to calculate because it's all marked by long distance QCD. And we have also the two interference terms that are the interference between the K short and the K long, and they're only between the L equals 0. And then we get this really cool formula that I'm really excited about. When you just look at this 4-1, you find the following relation. D squared plus D squared over D squared is actually this K long, the K short L equals 0, okay? So if you actually measure the CL and the interference term, you can get the clean short distance pictures of K short, okay? So that's the result. And again, it's come back to what I start my talk with. We actually have a very clean determination of, in principle, we can have a measurement of something that is very clean, and we can, using this, we can test the standard model. So exactly on time, that brings me to my conclusion. And with my conclusion, I'm just going to leave you with these two pictures to remind us what is next for the future for flavor. So the future for flavor is to look for BSM or to actually use the weak interaction to understand something about QCD. That's it. Thanks.
Thank you, Yuval. This was a great talk. We have time for questions. Maybe let me start asking a question. So one aspect of flavor physics that you haven't discussed in your talk is trying to explain what is sometimes called the standard model flavor puzzles, explaining where the hierarchies of masses and mixing angles come from. Can you maybe say a bit about developments in this area and what challenges are there in this context, maybe?
Yes. So clearly, one other thing that we are trying to do is to understand, there's so much structure in the flavor sector of the standard one, and we have to try to understand. And people, including me, had been working on this in the past, but unfortunately, I must say that I've been a little bit decoupled from this in the last few years, and I don't feel that I can tell you anything like smart about what's going on. And I'd be happy if someone can correct me, but as far as I can tell, a little bit from this side, there was no real great new idea in this direction of trying to understand the flavor of puzzle, but it might be just because I missed it, that there's something, the way I like to see what's going on in flavor theory, that people, of course, everybody try to understand what's going on with the anomalies. And when we actually go to the anomaly, many times we kind of forget about all this idea of try to explain things naturally and all this. There's a lot of kind of ad hoc assumption. But unfortunately, I just feel like I cannot give you an educated, nice answer for this.
Right, no problem. I guess the hope is that maybe if those flavor anomalies play out to be something real, that they might inform in some way what's going on with flavor in the standard model as well. But I guess one has to see how.
Yeah, so let's see, maybe Gudrun gonna educate us more about it. And the way I see the flavor anomalies right now is that it's rather ugly. I would say that I don't see any of them that actually make me feel like, it's really a nice solution. That would be really cool, because that's actually really explain like why we have these structures or something like this. But again, I don't know.
Okay, so now we have a couple of questions in the.
I have a question on the Q&A.
Yep. So it says, thanks for the talk. It was interesting. I have a question concerning QCD. Describing the SU3 breaking finer than one factor of about 20% seems quite important to me. Ideally, we could find some way to know how effects from SU3 breaking are the same or different in different processes. What is the progress here, or is this thought too optimistic? And are there measurements in particular that the experimentalists can provide that help here?
Okay, thanks. Yeah, this is clearly, very, very interesting. And that's something that I really spend some time on, and I feel on this I can get you something. So when we start looking in all these SU3 breaking patterns, what we start seeing is that there's some breaking that are actually bigger than others, okay? And we start seeing some patterns, okay? And sometimes we kind of relate this SU3 breaking into some what we call topology amplitude. And we see that, for example, when we have what we call the broken penguin, they tend to be larger than broken tree. And one thing that I hope that we can try to understand, and part of it is this big program that I hope that, something that I mentioned already, is that we are hopefully start actually measure SU3 breaking parameters. So when we work to leading order, we measure only the SU3 leading parameters. Once we start actually measure the SU3 breaking, first order breaking parameter, we start seeing some pattern. And maybe we actually going to understand something about, and again, one thing that we see that broken penguins tend to be larger than broken trees, okay? And that might be related to the fact that we actually kind of see that penguins or rescattering is actually larger. It's kind of larger than what we naively expect. So maybe we see something that, and it's maybe also related to the delta equal half thing in Keon physics, that when we have rescattering, it's actually larger than we naively expected in Charm and Keon, and maybe also in B physics. It's just larger than what we naively expect. And so I see it's part of a big program. We are at the beginning of it. I don't see we are actually made a lot of progress so far, but I see that we could make progress in the future.
Okay, and I see one more question in the chat. That's how well can lattice QCD determine weak decays?
B or D? Let me check.
I guess it's in general the role of lattice QCD in weak decay.
So of course, lattice QCD can do a lot of things for B physics. In particular, it can measure things like decay constant and some form factors. It can do things in one-to-one decay, so like B to D. But it's still very hard to do something that you have two particles in the final state. And we love to have it in both B and D physics, to have something like B going to KK or charm going to K plus K minus. I'm not an expert on charm. All I know that people are having ideas of maybe to understand some hadronic matrix element like D going to K plus K minus, which was what I was doing all this hand wave argument that I say, oh, I expect it to be order one. They expect to be able to do it. Now, who knows, 5 years, 10 years, but it's not from the out, as an outsider, I would say it's not hopeless.
Very good. So we are exactly on time now. So thanks again, Yuval, for the talk.
Thank you.